Hello, everybody. Thank you for taking time to join me for today's webinar. Today, we're going to take a look at remote actuated valve design and the concept of utilizing partial valve stroke testing. Now, I know there's a lot of strong opinions on this subject, but hopefully what we have to share here with you today is going to be thought-provoking and even helpful. We're going to take a look at various partial valve stroke test designs, both with and without automatic diagnostics. And we're going to compare those from a functional safety perspective. So if you have questions, please feel free to type them into chat. I can try to answer them during the presentation, or save them to the end and I can answer some questions then as well. So first, let me introduce myself. My name is Sean Statham. I've been in the industry for over 25 years, and majority of that time I've worked for OEMs that specialize in the manufacturing of valves, automation, and controls. I'm also a functional safety and cybersecurity professional. I have experience over that time in a lot of different roles. I've done some functional safety support for products for 10 to 15 years, product development, some engineering and design, and probably most importantly, application of the devices in the field. Really, seeing automated valve assemblies in various applications and industries all around the world. I've worked in developing process improvements, and for about 10 to 15 years specifically, I've worked on the development of improving the reliability of automated valve assemblies, specifically in safety instrumented system applications. I'm also a member of the NTIA Software Bill of Materials Development Group, and just a different range of experience in a lot of areas. Now, let's get to this partial valve stroke testing concept. Some people are for it, and others are dead set against it. I really don't know what camp you're in today, but we're going to take a look at it from the perspective of functional safety, and we're going to do some quantitative and comparative analysis, and it's really going to help you out. So we're going to talk about automatic diagnostics and why they're beneficial. We're going to talk about those automatic diagnostics and why we might want to implement them on final elements. We'll talk about partial valve stroke testing and diagnostics, and we'll really kind of go through the good, the bad, and the ugly. And we'll take a look at how the designs impact false trip rates. Now, you might be a PVST skeptic. Maybe you're dead set against it, but please give what we present here, some consideration. We'll do a safety and false trip analysis. We're going to look at various designs, and we're going to compare those designs. So we'll give you a lot of information to digest today. So, automatic diagnostics. The evolution of diagnostics in industrial automation really hasn't been without its challenges. Back in the 80s, two fundamental concepts were typically considered to improve safety: redundancy and automatic diagnostics. And the merit of those strategies, it was a real source of argument and discussion. I mean, really both then and even still today. Automatic diagnostics were definitely in the picture when IEC 61508 was being developed. And then over time, they've been used more and more to detect potentially dangerous failures and have really become the dominant technique used to improve functional safety. With the introduction of microcomputers, well, that brought significant computing power, made PLC architectures both safer and more reliable. And that really led to the powerful diagnostics we see today, where some designs can detect, good designs can detect over 99% of potentially dangerous failures. Automatic diagnostics have proven to be really the most cost-effective way to achieve safer safety and higher availability, especially in automotive and robotics and other industries where cost and weight are critical. So if we're going to look at applying diagnostics to remote actuated valve assemblies, we really need to first understand, the common failure modes. So starting here, we look at the valve and we see that binding is one of the main failure modes that increases torque required to close it. So if this assembly is part of a safety function and the valve doesn't close, we would consider that a dangerous failure. The seat and seal damage, that's also a big concern, a really common failure point, and that can result in process fluid leakage, which would be considered also a dangerous failure. And with the actuator, we know that maintaining pressure on the piston, that prevents the spring from closing the valve. So if we have chamber leakage through the seals and connections, we would consider that a safe failure. But if we have a spring break or spring sag, in which case, the valve doesn't close, then we have a dangerous failure. Looking at the controls, solenoid valve burnout is a significant failure mode that results in a safe trip. However, binding to the plunger or spool is a dangerous failure, as is, spring sag or spring break. And of course, a common failure we see is solenoid valve leakage, seat leakage, and that would be considered a safe failure. So, what kind of diagnostics can detect these failures? So looking here, we see, binding is absolutely detected by the movement of the valve. So we know that a partial valve stroke test does detect that. But unfortunately, when there's seat and seal damage that results in process fluid leakage, a PVST won't detect that. I mean, for obvious reasons, right? A PVST doesn't close the valve. The point of partial valve stroke testing is to stroke the valve 10 to 15% and not interrupt the process fluid. We don't want to stop the process, so we can do this partial stroke test, and we can gain some powerful information and data about the valve assembly without shutting down our process. The only way we can detect the seat leakage is with a full stroke test and the ability to sense seat leakage. If we look at the actuator, we see chamber seal leakage, a main failure point, and we can detect that with partial valve stroke testing that measures both pressure and pressure and position. We can also detect spring breakage with PVST and position pressure sensing, but spring sag can only really be detected with a full stroke test and pressure position measurement. When we look at the controls, solenoid valve coil burnout can be detected, not really with PVST. Binding in the plunger and spool mechanism can be detected with PVST and solenoid valve pulse test, but the solenoid valve spring breakage and the sag, that can only be detected really cleanly with a full stroke testing and pressure position measurement. Moving on to solenoid valve seat leakage, that can definitely be detected with PVST. So what do we see here? PVST, it's good, may not be perfect, but we see that utilizing PVST enables us to acquire some really critical diagnostics, especially when it comes to detecting some of the most dangerous failures. Is it worth implementing? Well, let's find out, and let's do some quantitative analysis to determine that. So I think we're finding, that PVST looks really good. It's one of the best automatic diagnostics available for remote actuated valve assemblies, and we've definitely seen that PVST detects some of the most dangerous and common failures. So you might be thinking, everyone's implementing it, right? Well, I think many of us know that's not the case. There's actually a lot of resistance to partial valve stroke testing. Now, after what we've already seen, some people might ask, well, why would that be? The main reason that people give for that is concern about false trips. Is that valid? Well, let's take a look. So a lot of field failure reports talk about, the early days of partial valve stroke testing. And in this first case we're looking at here, this was one of the early PVST devices that was tested by Exida, in an attempt to certify it. It had 1 out of 2 solenoid valves, and it was pre-programmed to trip on detected failure. And in order to test the PVST mechanism, we inserted a wooden dowel in the ball valve, and we initiated the PVST test. So when the valve hit the dowel, what we expected to see was a slight pressure drop, but the pressure went all the way to 0. The valve snapped the dowel, and it went completely closed, resulting in, you guessed it, a false trip. And with this particular design, every time there was excessive resistance or binding, the actuator would go all the way to 0, and we would get a false trip. Now, we saw another PVST concept that was designed by a valve integration company where they used a logic solver, I suppose save money, and they used the logic solver to de-energize the solenoid valve while using a position feedback switch to monitor the valve's movement. So when the valve moved, they would re-energize the SOV. It seemed like a good idea. Seemed like it would work. Well, in our test, the switch failed closed. The PLC kept the SOV de-energized, vented the actuator completely, and again, we had a false trip. We've also seen a lot of engineers design PVST that's configured to trip on diagnostic failure. But our analysis has shown that this again results in false trips. So imagine being the process engineer that has to explain to management what happened on this expensive false trip event. I mean, really, if that was me, I might never use PVST again, honestly. I mean, I've met a lot of people that feel that way. And if that's you, I encourage you to listen further, and we're going to continue to investigate this together. So when it comes to partial valve stroke techniques, one of the main things we've learned is that the pressure to the actuator must not be allowed to drop too far, right? So a good PVST design will not allow the pressure to drop below a set limit. We've also seen that a good design does not trip on diagnostic detection. It's best if diagnostic detection results only in a failure annunciation. We've seen that 1 out of 1 configurations are best if we need 1 out of 2. It's really better to duplicate the entire assembly. It's also been shown that if we set the PVST for automatic operation, it reduces binding and reduces the potential for stiction. The PVST movement should occur at least every month. So studies have shown that, really this significantly reduces binding and also reduces the chance for false trips. So on the right column, when we look at bad designs, we see false trip rates increase when we configure the trip on diagnostic detection. Why do we use 1 out of 2 configurations? Well, a lot of people have told me the answer to that question is because it's just what we've always done in this plant. Well, 1 out of 2 doubles the trip rate contribution of the device. Another problem arises when we design the device to allow the actuator to go to 0. And here we see the potential for another false trip. Unfortunately, we see, a lot of bad designs pretty consistently. I mean, well-intentioned, meant to improve safety, but they could be improved. And when we consider the fact that our design introduces the potential for false trips, we see that we're not only, we're not actually improving safety. So let's take a deeper look and see if that's true or not. We're going to do some quantitative safety and false trip rate analysis here. And what we've got in our example is a spring return Scotch yoke actuator with a triple offset butterfly valve, 3x2 solenoid valve, smart positioner, volume booster, and filter regulator. And we're going to be using failure rate from Exida's calibrated FMETA and proof test coverage. So that's where we're going to get our data. And really this, in Exida's experience, it's proven to be very realistic data. So it gives us a great opportunity to do some deep dive comparison. For our analysis, we have to make some fundamental design comparison assumptions, and you can see those here, and they're pretty basic. You know, it's solenoid valve de-energized trip. It's a fail closed application, but the main thing I want to point out here is, or at least note, is that we have determined the average cost of a false trip is $500,000. So we're going to be using that to calculate some of our costs. So let's start out with this simple 1-out-of-1 design with spring return Scotch yoke actuator, triple offset butterfly valve, 3x2 solenoid valve, and we're going to assume the solenoid valve vents the actuator when the coils are de-energized, and we'll have a filter regulator. So we have the devices listed here along with their calibrated FEMITA failure rates and the proof test coverages. We're going to run the calculations in Excellentia based on the assumptions that we looked at on the previous page. And we're going to see failure rate or false trip rate. In this case, in this example, it's 7.55 e to the minus 7 failures per hour. So if we take the probability of a trip given in a year times the cost of a trip, that gives us the false trip rate cost per year of $3,307. So our dangerous failure rate, you know, the one people really put the most focus on, is 1.34 e to the minus 6 failures per hour. So the probability of failure on demand, you can see here it's 0.0196. So we're at SIL 1, you know, based on IEC 61508 tables. Sample number 2. What happens if you follow the design specification that's been recommended in your plant and you implement a 1-out-of-2 redundant solenoid valve setup? Keep the rest of the design 1-out-of-1, but go with 1-out-of-2 redundant solenoid valves. Well, when we add up the safe failure rates on this design, we see a 1.27 e to the minus 6, so it's a bit higher, but now our false trip has increased and our cost has increased, I mean, pretty significantly. Not good, right? But we improved the safety, right? Because that was our goal. Well, how much did we improve safety? Our dangerous failure rate is 1.17 e to the minus 6. So the probability of failure on demand was 0.0188. I mean, very, very small improvement in failure rate, but a large increase in false trip rate, resulting in a pretty big increase in cost. So did we achieve our goal to make the design safer? Well, we had a relatively insignificant improvement in safety. We had a much higher false trip rate and increase in cost. Going to 1-out-of-2 solenoid valves may not be really the best solution. In our last webinar, we suggested there's ways to optimize safety without increasing the false trip rate. And you're probably thinking, if that's the case, prove it, right? What design can do that? Well, let's see. So we'll start by adding a PVST controller, and we'll have it configured to trip on a detected failure. So why are we going to do that? I can't tell you how many times I've heard the response, because here at our plant, we always configure our designs to trip on detection of failure. We do that because it's way safer. Well, if that's so, let's find out how much safer is it. Take a look at the failure rates. Now, since we've implemented PVST, some of the failures are detected and some are not detected. So that's a change from our previous examples. Running it through Excellentia, we see a safe failure rate of 1.7 e to the minus 6. But now we see the false trip rate and cost has skyrocketed. I mean, it's $7,437. But that's okay, right? Because we increased the safety. Well, our dangerous failure rate is 1.28 e to the minus 6. And the system has a probability of failure on demand of 0.01596. That's really not that much better, right? All right, well, let's try another configuration. And this time, not to trip on detected failure, but to enunciate on detected failure. Same design, same hardware, excuse me, same failure rates, but we're not going to trip every time a failure is detected. So now we see a safe failure rate of 4.87 e to the minus 7. And the false trip cost per year dropped, dramatically dropped, actually. Look at that. It's $2,133. Our dangerous failure rate, 1.28 e to the minus 6, excuse me. And our PFD average is 0.01598. So our failure rate is virtually unchanged, but our false trip rate and our cost, that's way less. All right, we'll talk more about the comparison later. Moving on to the next design, let's say that our smart positioner didn't have the necessary capacity to stroke the valve. So we have to add a volume booster. We can probably expect a slightly higher failure rate adding the volume booster, and after running the numbers, it does go up slightly. Our safe failure rate is 6.17 e to the minus 7, and our false trip cost has gone up slightly. It's $2,702. Our dangerous failure rate is 1.33 e to the minus 6, and our PFD average is up slightly, 0.01607. But we're still one. So we see that even adding the volume booster, we significantly improved the safe failure rate. And compared to some of our earlier designs, we've reduced our false trip rate and our cost. So we see here that we don't have to trip on detection of failure to achieve safety, right? So let's compare all these designs. So let me ask you guys, what design is going to lower the false trip rate and deliver the safety here? If I compare it to the simple 1 out of 1 design, I see that it had a false trip cost of $3,307. Wasn't the best. 1 out of 1 with PVST controller configured to enunciate on detection of failure it's clearly the best. Even if we had a volume booster, we only increased the false trip rate a little bit, not a significant amount. And we're much better than the example 1 out of 1 on false trip. We're a whole lot better than some of the other designs. Wait a minute. Our objective with the other designs was to improve safety, right? We'll take a look at the PFD average column. We started out with a 0.0196. We chose to put in 1 out of 2 solenoid valves on our next design, and wow, we didn't improve safety much at all. Cost went up. We put in a PVST with trip on detect, and that was, the best of our designs from a safety standpoint, but the false trip rate and the cost skyrocketed. Now look at design number 4. We had to go out 4 decimal points, really to even show a difference. And look at the false trip rate and the cost. That's amazing. Even when we added a volume booster, it's really not bad. So what are the best designs? Obviously, it's the last 2, right? If we can add partial valve stroke testing and enunciate on detect, we really optimize our design with the lowest false trip rate and the best safety. So there's some other design comparisons we can do, and we might do those in upcoming webinars. And the one thing we know we don't want to do is utilize designs that increase the false trip rate, right? So what are the conclusions we can draw from our analysis here? Many good actuated designs can be improved with the application of a well-designed partial valve stroke test. When we automate it to take place every month, that's great. And if we can automate it to take place every week, that's even better. So what we've seen is safety can be improved and false trip rate can be improved. Interesting results. So that's what I have to share with you today. Let's see if there's any questions. I don't see any questions today. Well, thank you all for your time. I really appreciate you attending this webinar. If you have any other questions, you're welcome to email me at sstatham@exida.com. You're also welcome to go to our website. We have a tremendous amount of resources there to support you, information, white papers, other webinars. If I missed any questions today, I can come back and answer those. I'll get those via email and I can answer you back. So don't worry about that. I'll get the questions answered. Thank you all for your time today, and appreciate you being here.